Hello everyone. Thank you for joining today's presentation. Our work is titled A Comparative Analysis of Machine Learning Algorithm for Intelligent Spectrum Sensing in Cognitive Radio Network. This research is presented by myself, MD Tofal Ahmed, along with my co-author Moshumi Haq, Yusake Sugiaro, and Tichua Shimamura. To guide our discussion, here is our outline. We will begin with an introduction to cognitive radio and the motivation for our work. Then we will discuss both conventional and modern machine learning based spectrum sensing model. I will walk you through our model implementation, share the key simulation result, and finally present our conclusion. Yes, let's start with the fundamentals. Cognitive radio is an intelligent wireless communication system. Its core function is spectrum sensing. It constantly monitors the radio environment to identify which frequency band are occupied by licensed primary users PU, and more importantly, to detect the ideal spectrum holes. Those holes can be safely used by unlicensed secondary user SU, improving overall efficiency. Why this so critical? There are two primary reasons for this critical situation. First, the demand is exploding. Recent data shows over 35.85 billion wireless devices are connected. Second, regulatory bodies like the Federal Communication Commission FCC in USA report that up to 90% of the licensed spectrum remain unused at any given time. Cognitive radio is the key technology to bridge this gap between scarcity and underutilization. How do you perform this spectrum sensing? Traditionally, we have popular conventional method like energy detection and mass filter detection. However, each method has specific requirements and face challenges, especially as we demand higher accuracy in difficult conditions, which increase computational complexity. Let's dive into the core statistical model behind spectrum sensing. We frame this as a binary hypothesis testing problem. H0 mean only noise is present. H1 means signal plus noise. We evaluate detector using two key metrics: probability of detection, which should be high. PD is the probability that the detector correctly identifies the presence of PU when it is truly there. And the probability of false alarm, PF, which should be low. PF is the probability that the detector incorrectly identifies the presence of PU when it is not there. In a conventional system, every method is decided by the comparing a test statistics to a threshold. Why do you need machine learning in spectrum sensing? Conventional method like energy detection come with a serious drawback. The conventional method are noise sensitive and cannot classify signal, depend too much on threshold, and ignore the key feature which make them unreliable for modern spectrum sensing. Machine learning overcome those limitations. Diving deeper into the conventional method, while useful, has limitation in low signal to noise ratio SNR environment and under the noise uncertainty. In such an environment, machine learning excels. Machine learning model can learn complex pattern, operate better in low SNR, and even classify the types of signal present. However, a major challenge remains. Their performance is heavily depend in the quality of a dataset. Let's discuss the motivation behind this research. Currently, most research in ML-based spectrum sensing focus on limited set of popular algorithms. We identify gap, a lack of comprehensive systematic comparison across a wide range of models, including both classification and regression approaches. Therefore, our goal is conduct these broad analysis to provide clear guidance for optimal model selection. Why we build our dataset in MATLAB using 4 QAM signal in AWZN noise from -19 to 11 dB SNR. Each observation is transformed with FFT, and we extract energy and standard deviation feature from the real and imaginary part. These provide us a 5-dimensional feature vector labeled 0 for noise only and 1 for signal present, which is ready for machine learning training and testing. We test two main approaches. The first is classification model like SVM, DT, and NN, which directly predict whether a PU signal is present or absent. The second is regression model like SVM regression, Gaussian process regression, and a logistic regression, which output a continuous value that we then convert into a decision using a simple threshold. This setup allows us to evaluate which strategy works best for spectrum sensing in different scenarios. This flowchart illustrates our end-to-end machine learning pipeline for intelligent spectrum sensing. We begin with dataset generation and preprocessing, where we simulate signal, extract feature, and prepare the training data. Next, we move to model training, where multiple classification and regression models are trained simultaneously for a comprehensive comparison. Once trained, each model enters the evaluation phase, where we measure key performance metrics like detection probability and false alarm rate against the test dataset. Finally, based on this evaluation, the system makes a sensing decision, selecting the best performance model to deploy for real-time spectrum detection. All of our work was done in MATLAB 2023A on a Windows 10 computer with 32 GB of RAM and an Intel i7 processor. A key point is that we did not use a graphical processing unit GPU. All result came from the CPU alone, so our performance data reflects pure processing unit. Now let's walk you through the exact step of how we implement and train our machine learning model. Our dataset is simulated with input signals for QAM AWZN channel across low SNR values from -19 to -11 dB. We split the data 80 by 20 for training and or testing. Normalize the feature and train models using MATLAB function like the speed SVM function for classification and feed RSVM function for regression for SVM. Predictions are made with the predict function, and performance is evaluated using metrics derived from the confusion mat function, including accuracy, precision, PD, PF, and sensing error. Let's look at the result. First, this scatter plot shows a snapshot of our training data at a very challenging SNR of -13 dB. You can see the distribution and overlap between the signal present and noise only cases. We set as challenges for different classification models to accurately identify the PU. The performance is best summarized by the receiver operating curve ROC. at that same low SNR. As you can see, SBM regression achieved the highest area under curve AUC at 95.98%, closely followed by the SBM classification and neural networks. Decision tree model, while slightly lower, still performs at an acceptable level for particular use. At slightly higher SNR of -12 dB, we see the accuracy matrix. The top performance in this test are the binary Gaussian kernel BJK with logistic learner classifier and neural networks for classification, as well as Gaussian process regression and neural network regression for regression tasks, all of which achieve around 94% accuracy. The generalized additive model, or GAN, is the weakest in this test set. But accuracy is not everything. We must consider computational cost. The simplest model, like decision tree and the naive Bayes, are the fastest to train and test. The most complex model, like Gaussian process regression and neural network, offer high accuracy but a significant cost in memory and processing time. Linear models provide an excellent balance of adequate speed and reasonable performance. In conclusion, our comprehensive analysis shows that both classification and regression model are highly effective for spectrum sensing. For top accuracy, consider SVM, neural networks, and BZK classifier. If you need a balance of performance and efficiency, simpler linear model are strong choice. The best model ultimately depends on your specific system requirements, such as whether you prioritize absolute detection accuracy and computational resource. That concludes our presentation. Thank you for your attention. We are now happy to take any question you may have. Thank you very much.